an equation-free based coupling approach for long-term cryogenic tank behavior predictions. And the presenter on this is Shanbin Shi from Rensselaer Polytechnic Institute.
Good afternoon, everyone. And today I will be talking on equation-free based coupling approach for long-term cryogenic tank behavior predictions. And my name is Cheng from Rensselaer Polytechnic Institute. And first, I will briefly talk about my research background, and then I will introduce the equation-free modeling, and we propose the equation-free based coupling approach. And I will talk about the research objective, and then I will show like two applications using the equation-free based coupling approach. One is the pipe flow, and the other is a cryogenic tank. And then the conclusions. As we know, like the cryogenic storage tank is widely used in NASA space missions, like for propellants and some like life support consumables, like liquid oxygens. But there are heat leaks from surroundings, like the radiations or some structural heat leakage, and this will lead to excessive tank pressures, and we call this like the self-pressurization process. And also, we need to depressurize the cryogenic tank, and now we prefer, comparing to like the original ventilating method, we prefer some active cooling method like the jet injection. But if we look like if we look through this whole process as shown here on the right hand side, both the temperature and the pressure inside such a cryogenic tank, there are two very significant characteristics of these two evolution curves. Like we can see the dashed line is experimental result. As I remember, this should be from MHTP tank. And during the pressurization, there's going to be like a relatively long time to pressurize the tank. And then we see many similar cycles for the heating and the pressure depressurization cycles. And we like active cooling, and the pressure will decrease a little bit. And then after a while, it will like self-pressurize again. And we have so much similar cycles, and we can assume like most probably the similar cycles means like they are undergoing similar physical process. But although the cycles are similar, but we can see like the starting point and the ending point wouldn't be like the exactly same. There should be like some fluctuations. So for this periodical behaviors, we see like there are similar heating and depressurization cycles and the disturbed initial or boundary conditions. And this is the basis for our equation-free based coupling approach. Like there are some complex phenomena in microgravity environment, like the thermal stratification, especially very significant in the evaporation, and also natural convections. So we need fast and accurate numerical tools for long-term tank behavior predictions. And we know the high-fidelity CFD simulation is computationally expensive, but the fast nodal code simulation lakes like fine scale details inside the lumps, because everything inside the lump is uniform. So for within one lump, all parameters are the same, and there's no distribution like velocity or temperature distributions. And the flow patterns inside the lump will affect the heat transfer for like the natural convection. So we prefer the coupled method, and the coupled method is designed to combine advantages of both approaches. And for the equation-free modeling, the initial design of this equation-free modeling is to use a microscopic simulator to obtain macroscopic solutions with reasonable computational cost. And there are some assumptions like we have an accurate macroscopic simulator exists, and the macroscopic evolution equations are unavailable in closed form. And but macroscopic phenomena are more important. The original example for this is like in chemistry field. Like we know there are molecular dynamic equations are very accurate, but it's impossible to use it to simulate some real chemical reactions. So they developed the equation-free modeling method, and this method, the basic time stepper they call the macroscopic time stepper. And the first, given the macroscopic initial condition, the capital U at time k, time tk, and create the corresponding macroscopic initial condition, the small u at tk. And then we can run the microscopic simulator over a very short interval to obtain the ut within, like see in the right hand side, the right curve. We use the microscopic simulator and run for this very small time interval. And we based on this microscopic simulator results, we construct the corresponding macroscopic evolution ut within this time interval, and then we extrapolate the macroscopic result to the time tk plus 1, and then we finish one time step in the macroscopic scale. And we can adapt this equation-free modeling idea to coupling approach. Like in equation-free modeling, they don't have any kind of like macroscopic simulator. And they do have the microscope simulator, and the microscope simulator will be used in each time step to construct the macroscope result and then extrapolate within certain time step. And now we look through like our problem. We do have a nodal code which can be treated as a like macroscopic simulator, and we also have like a more detailed high fidelity CFD code. So our equation-free base coupling, the basic idea is we use the nodal code as the macroscopic simulator, and we run the nodal code for the full-time domain, but we do run the CFD code for a short period, and then we compare the result within this short period to obtain some equation-free corrections for the nodal code and to extrapolate the corrections into the full-time domain. And the reason we can do this because like we assume the CFD model is accurate, but we can see derived convert equation between the two codes is impossible. Like for CFD code, we can see the volume average governing equation because we know the nodal code, we can only get result within one node. So when we want to compare, for example, the temperature, we need to calculate a corresponding volume average temperature in our CFD result. So the governing equation of the CFD result is shown here, and the governing equation for the nodal code is shown here. And it's really impossible to derive a convert equation to convert our nodal code result into CFD result. And we can see clearly like they do have some difference. Like first, they denote the flow rate, and this is the flow rate term in nodal code. But we can see because the CFD code is like more like the calculated result and then calculated average, but the nodal code is a like average level calculation. So there must be difference. Therefore, we can adapt the equation-free idea to find the conversion correlations, not the accurate convert equation, but the equation-free based conversion correlations to solve this problem. And because we know there are periodical behavior of the cryogenic tanks, so our equation-free based coupling approach will co-solve for the first cycle to get the equation-free corrections. And then we can use the nodal code for the rest of similar cycles with corrections. And the corrections are obtained through the on-the-fly co-solve process like we shown here. Like for the time t and within a very short time period, we run the nodal code and the CFD code together, and we compare the result within the short period to get equation-free corrections. But the nodal code will run until the end of the problem, and then combined with such kind of corrections, we can get a corrected like CFD-like nodal code solutions. And the best advantages of this kind of coupling method is comparing to the like the domain decomposition, whether in spatial or time domain, there is no 1D, 3D data transfer error. And comparing to the original equation-free modeling approach, because we do have a macroscopic simulator as the baseline of our results, so we can expect a better performance by introducing these nodal code solutions. And our object is actually efficient use the CFD and nodal code tools based on the equation-free based coupling approach. So first, we're gonna feed the data within the first cycle, the co-solving period, or within a first at the beginning a short time period, and then we're gonna extrapolate the corrections to the rest of the time domain with a disturbed conditions. And our first example is a pipe flow with periodical pressure boundaries. We can see it's a internal laminar flow of a strange circular pipe, and the liquid is water. And we design a periodical changing inlet pressure to mimic the heating and heating depressurization cycle. And we can see here, this is the total gauge pressure of the inlet. And we can see the to demonstrate the ability of this approach, we change the starting point and the ending point of the pressure of this pressure curve, and we keep the outlet pressure equals 0 for the entire problem. And within see, there are so many circles, so we're gonna look through the first cycle to get the equation-free corrections. And we can see the result of the first cycle. The nodal code is over predicted the average velocity due to the difference of, because the CFD code will consider the hydrodynamic entrance effect, but we didn't add this as extra correlation. We just use the default setup of the nodal code. So there is a over prediction of the average velocity in the nodal code, but then we compare these two results and we can find a linear correction like shown here to correct our nodal code result into a CFD result as the green line here. It's not surprise because we feed this data together. So the green line is much more similar like the CFD, the blue line. But when we extrapolate the same linear correction to the whole problem, we can see the result is excellent because we only use CFD results for this first 20 seconds, and for the rest of problem, the conditions are changing actually, but we can use the same linear corrections to correct the whole nodal code result, and we get a new result. We can see it's almost overlapped with the CFD results, which shows that this method is very efficient. And we have to note that the computational cost will be reduced significantly because basically we are using the nodal code only with with a very short time CFD result. But this pipe flow is more like we can draw a conclusion that this correction can correct the hydrodynamic entrance effect in that geometry within a certain range of fluid parameter changes. And the Reynolds number actually goes slightly beyond the laminar region. So it's a little bit robust for these corrections. But somehow this pipe flow is more like a point-wise correction because the average velocity is the same within the whole pipe. And if we go into tank problems, we assume the CFD results at time t, we should have a position R and the corresponding nodal code. So will also be assigned a position R. So our correction will be, instead of only one linear correction, we're gonna have a position distributed equation-free corrections. So we design a cryogenic tank cell pressurization problem. As we can see here, they are liquid and vapor nitrogen and with a 75 filling level. And the initial pressure is 100 kPa. And the initial temperature is a saturation temperature under this pressure condition. And we set the adiabatic set and bottom walls, and there are heat flux from the top of the tank. And there's no inlet and outlet, so the tank is pressurized. And we designed two different cases. First, we use a 50 watts per square meters of the heat flux, and with a flow time of 100 seconds. And the other, we increase the heat flux into 80 watts per square meter and the flow time is extended to 200 meters. So we want to co-solve by using the nodal code and CFD code in case 1 and find the equation-free corrections. And we then extrapolate these corrections to use these corrections for the case 2, the increased heat flux and the extended flow time, to see whether the same correction works well with a different situation. And we can see the result of the two code. First, we use the single fluent as nodal code, and the CFD is ANSYS fluent. And we can see we divided the tank into different regions to compare the two results. I only show the first 5 results because we can see like the green line represent the 4th region and the dark red line represent the 5th region. They are almost overlapped. So below that region, especially in the liquid region, the results, the difference between nodal code and the CFD code is very small, so we cannot see any different. But we see for the upper region in the vapor, there are significant difference and also significant thermal stratifications. The nodal code overestimated the temperature of the tank. And now we use the linear regression, and we use we can see the phase diagram of the first region. We use the log to normalize our result, and the x-axis is the log nodal results, the log nodal results of the temperature, and the y-axis is the log CFD results of the temperature. And we can see we just use linear regression to feed a linear corrections of these two results. And this y equals our the CFD nodal result, and this x represents our x-axis, the nodal results. And we use this one. We use the same approach for every regions, and then we can have a corrected result comparison of this 50 watts per square meter heat flux. And we can see this X marks represent the corrected result, and they are much more better compared to the original one. But again, because we feed, so these results are, we should have such kind of result. And the real problem whether we can use the result to disturb the initial boundary conditions we designed the 80 watts. So we still use the same equation-free corrections for this 80 watts per square meters. And we can see the dashed line represents the nodal result, and the solid line represents the CFD result. The cross marks represent the equation-free based coupling result. And still, the corrections are obtained from 50 watts per square meter cases, but it can use in the 80 watts per square meter cases, and also it can be extended to double the time from 100 seconds to 200 seconds. So which means we are not just manipulating the data. We do find some corrections with some physical meanings. So the equation-free based coupling approach is capable to correct the nodal code results with disturbed conditions, and it's very easy to apply the computational efficient and computational efficient. And there is no 1D 3D data transfer error. So our planned activity is we need to use the equation-free coupling approach to tank with the heat depressurization cycles, and that's our basic idea whether we develop this method, because we know if we can deal with the first cycle based on the result we show here, we should be able to deal with the rest of the time domain. And we need to validate the coupling approach with experimental data. And this work was supported by NASA ESI program. And I also want to appreciate the CR Tech staff. They offer me the single fluent software and give me so much support. And I want to say thank you to them. And thank you, everyone. I appreciate it if there's any comments and questions. Okay, the question is why I use Nitrolux to normalize the temperature. Yes, that's a good question. The reason is actually, for almost all numerical tools, they will, let's see, for example here, although we have governing equations like this, but in the end, they will linearize all this kind of governing equations. And in the end, the solver will solve a linear system like the, for example, the temperature. The temperature for like time step k plus 1 equals a matrix times temperature time at time square time step pk. Like it will be a linear system. So the equation is more like x equals ax, something like this. So if we our equation-free based coupling approach want to correct the parameter matrix, the A. So if we use the natural log, we can like get this A as the parameter. So we do this normalization, and we do see a like more stable result after using this law. It's more like this one is the linear regression, but for both CFD and nodal code, they are almost solving the same linear system like this. And the difference is this on the left side, it will be like the temperature at time step k plus 1, and the right hand side will be the temperature at time step k. So when we use the law, we can get the parameter matrix A, and then we are correcting this matrix, so we get a better performance for our approach. I hope that can answer your question.